And we are live.
And we are live. Awesome.
Hello, everyone. This is what we have planned. We'll see how deep we get. Jonathan's going to show us a very important visualizer for how to go back and forth between PCA features and original space features. And for myself, because of my use of eigenspace in two different other fields besides data science, just felt that was super important and is not being emphasized. And no one had taken this more seriously than Jonathan. And we're going to let him share what he learned from that encouragement. And hopefully you guys can all add it to your arsenal of tools. Go for it, Jonathan.
Go for it. So find the video disappeared. Find the share button now. Share my screen, and there we go. That should be visible. So yeah, we can use the PCA to in our data sets. Is very useful in some more larger data sets, and definitely we can use PCA to find the most significant features. Also, if we have a high presence of the multi-collinearity, and then it can help us reduce the computation and training time once we've done our feature reduction using PCA.
And Jonathan, I'm sensing for your example today, you're going to use the Titanic data set. I'm picking up that vibe from the language of the features. Okay, good. That's even better.
Yeah. So actually,
and I'm going to ask Jonathan some questions along the way. So I would normally think to use PCA for regression type problems or continuous type problems, but here you are using it for a classification problem, correct?
Yeah, correct.
Okay.
Yeah. So this is actually already been cleaned up from a previous Python script. It's gone through, and I've saved the clean CSVs. So, and the most important thing when we're using the PCA as well is that everything is normalized. And if we're using it for the classification, we give either the ones or zeros, or give it a number within the range. So if we've got some groups, we can number the ranges 1, 2, 3, for example. But we have to normalize it and keep everything on the same playing field.
And when you say normalizing, you obviously, I mean, as we all know, that's a great term for what Jonathan's talking about, but we have a lot of terminology flux in the data science realm. So you also mean by that scaling, correct?
Yes, correct.
Okay, good.
So here you can see it's all scaled, and also the other thing that we need to be careful of once you do have it scaled is that you do drop one. If you're using dummy variables, that you always drop one.
Okay, so this is for those. What I sense you're saying is, hey, the Titanic data set has a lot of text.
Yes.
And so you got to one-hot encode it, and one-hot encoding gives a column for every one of the words that appears in a feature. So in other words, if you had one feature that was text input, it would take the unique instances of those text values and create a new column for each one of those.
Yeah.
However, the case where if you drop one of them, that gets rid of some mathematical issues. And the cases where a row says 0, 0, that covers the case that you dropped.
Yep.
Excellent. Okay. Very good. And I agree.
Yep.
So go for it.
So what we also should do we're also with PCA is to make sure you have all your features in. Don't take anything out, just leave everything in, to get a better accuracy from when you're using PCA. So it's important that you keep all your features in there.
Excellent. Okay.
So just like with the sklearn logistics regression or classification regression, we do exactly the same part there. So we can call our model, but instead of calling the logistics regression, we're going to just call in the PCA component.
And Jonathan, are you planning to add this code to the course repo?
Yes, I can do. Yeah,
that would be great. Excellent. Now, Jonathan, from your perspective, and I'm not asking you to regurgitate things I've taught you, I'm asking from your perspective, why do you think it's important to scale your features before you go to PCA?
Good. So if you don't scale it, you can have a huge what's the way? You could have a very wide range in your feature weights, and then PCA could value the higher weighted value from that feature, and then cause bias in its computation.
So like you were saying, put them on an equal playing field. That's so you get an accurate indication of what features are truly important to the predictions, both in the original space and the PCA space.
Yeah, correct.
Now, so also, well, let me let you go on and we'll cover it, because once we view the PCA space, features in PCA space and the eigenvalues in PCA space, we get some additional insights, correct?
Correct. So what PCA would do is kind of like score or give a percentage of the significance of each feature, and we can loop through, and then we can also choose how many features do we want, or how many PCA components we want to have a look at. So generally we're going to say, okay, let's have 7. In this case, we'll have look at 7 PCA components, as we have 7 features, and we'll run through it 7 times and see which features are going to start become more significant. And then when we can run our model on only the first 3 PCA components, or we can say, look at the end result and say, well, these features are significant. I will keep these in my data set, drop the rest, and then run with those features in our modeling. So I think, so when we're going to go through just like with this is a little bit of a backwards chart to what Tom showed last week, and it's showing our cumulative explained variance, and you can see as this would start curving or starting to flatten out at the top, we can see which PCA components is more significant to our model. So already when we look at this, we can see 80% of our for our significant values fall represented within our first 3 PCA components.
And I love this visual, Jonathan. Very well done.
And then when we go down here, we've got the values, so we can see the first 2 PCAs, we've got a weight of 40% and 30% alone. So that's almost 80, and then we can take the third one to say, okay, well, this is our 80%. So we're looking quite strong on those first 3 components.
Now let me ask, please. The way I read this, then we've got 7% in the 4th spot, and about 6% in the 5th spot, and about 3%. has this already been reduced by what you learned through PCA? Like, were there some other ones that were adding up very tiny off to the right, and you've already removed them, or this is the, I can't remember.
Yeah, so this one, this one, I said, okay, I want to start off with this size data set.
Okay.
There were one or two other columns, but they weren't really representative of anything to do with the data.
Okay.
For the model.
Got it. But did you reduce the feature set based on your PCA analysis?
On previously,
else?
yeah, previously. So this one's kind of a semi-worked,
okay,
semi-worked project. Yeah.
So the steps off to the right in your graph there, they just get tinier and tinier. PCA does that for you, and then you can now it only applies in PCA space, right? But you can eliminate those super small ones. But it looks like all of these have good significance levels.
Yeah, correct.
Okay. But yeah, so there might have been an 8, a 9, a 10, an 11, a 12 that were tiny over here on the right.
Yeah. So it's just literally the inverse of the one example that you showed last week, where it started off small and then grew.
Very good.
So yeah, so just as explained, we're seeing that so that our first 3 PCA components collectively are showing 79% of the classification. And then what we can do, so now we can look back into what features were causing had the most significance in each of the PC components. So we've got now, from going from the space, we're now going back to original features, but pulling the weights of each of those features within the PCA space.
Okay, Jonathan, maybe this step will explain the question that coming on the chat from Haitish. The question I will mention it now, and also I will add to it another question. The question from him is, how do we interpret these transformed feature? So we know what age column contains, but after transformation, what do the numbers in that transformed columns means? This is the first question, which is from Haitish. From my side, when we moved from the original space to the PCA space, what we performed truly, why in the PCA space we are able to find, let's say, kind of ranking for the significance of the features, why this has appeared. If we are able to, I'm always looking for the, let's name it the magic word. Do we have magic statement to explain the PCA, regardless of the technique itself?
Regardless of the technique itself. Well, how can I?
I have intuition. Maybe it can help, and then Tom can correct me because maybe we are moving to the space that represent our task in let's say most of our findings with the less amount of components. So that's why we are able to find this, let's say, significance in the components. That means we are able to split it. We are able to find kind of explained method in the let's say BCA space, not in the original space. So maybe this transformation is finding the suitable space that explain a lot of the tasks. This is my intuition. It's up to you.
I want to hear your answer, Jonathan, but I can help you out on this, I think.
Yeah, so I know how, just trying to I know it, but I can't put it into words.
It's hard. It is
yeah.
hard. Well, what's fun.
Like it's like, yeah, it's measures the distance and the spread. It just takes it all and separates it away. I'm just trying to, yeah. I know it, but I just can't put it into words.
Let me try first, and then you follow up with what you were thinking. But it's this spirit. When you look at it mathematically on a large scale, the most efficient way to do this, it's a technique of finding a series of rotations that create a complete independence between the features or the inputs, so that there's absolutely no collinearity, or it's been reduced to some minuscule, insignificant amount based on noise. And then these get ordered by what are called eigenvalues. Now, just to give you an appreciation for what the eigenvalues are, they're, depending on the type of realm you're in, it deals with a type of oscillatory value. So it's saying that basically a variance when you get down to it. What is and it can go into complex space, by the way, but what is the variance on this particular feature? And so the most significant variance is obviously, well, hopefully, obviously, a feature, not a noise. And so it says, oh, well, that is my largest PCA feature. And then it looks for the next oscillation or variance. Now, to give you an appreciation, when you apply this to mechanical vibrations, or really vibrations in any realm, we have oscillations. It is in the frequency domain where you're getting those oscillations. Those are your eigenvalues. And I hope this helps also. The eigenvectors, if they're scaled, and they're usually scaled, if you apply them to that system as initial conditions in order according to the state variables, it will excite just that one mode. For example, if you hold your guitar string just right and pluck it, even though it's this long, it will create two nodes because you created a middle one. Or you put it you put your finger just right place to get the third octave, then it'll do in three places. It's similar to that. You're creating these initial conditions that excite only one mode. So, but this is a generic mathematical trait that we're talking about. So it gets the highest variance, then the next highest variance. And for each of those variances, there is an eigenvector that will put the system in that single state.
Yeah.
I hope that helps.
And this might help even more.
Oh, excellent.
So yeah, so here this is one showing height and weight, and so this is what one resource that I like to have used when we was doing some parts earlier, looking at the PCA, and then it's showing you how it will plot from the original data set into the PC components. So as Tom mentioned, as you move zoom in on one feature, and start, or one value, and start moving it, you will see how it takes the spread in the PCA. So as you see here, you start seeing the variance, and then you see how the others start to cluster separately. So then you can start moving from your values in the original data set, and you can see how the variance and how they start to cluster together.
That is beautiful. And Hitesh, I think once Jonathan shows how you relate the eigenspace, the features in eigenspace, to the features back to original space, I think your question will be perfectly answered by the visual he's got coming up.
Yeah. So then this is the 2D look, and then if you go down here, then it will show you in it in the 3D space, and then here you can show So you see it here that it's still clustered. Everything is 0 on the PCA. And then here, when you show the PCA model, you can see how PC1 has the significance of more significance than the other PC components. So I can link this also in the chat. So, and it goes on a little bit further, just some other examples.
And for those that are listening to the replay, and also for Hitesh, if you master this understanding at the 2D and 3D level, it will help you just conceptually appreciate hyperspace examples when we go beyond 3 dimensions.
So what we're now pulling here, so we're going to start taking the percentages of each PC component. So we're saying, okay, we want to take all the components, and we then saying what our columns are, and we're going to take which PCA we want to have a look at. So if we wanted to look at more PC components, we could put 8, 9, and 10 if we had them, or you can reduce it just to see where they are. So you could potentially say, well, we already know that 80% is in the first 3 components, so we could only look at three of them. But if we, in this case, we can say, well, we want to have a look at all our components and see the weights of each feature. So this is just the tabular form. So in PC component 1, we can see the passenger class is 12, has 12%, sex is less than 0%, but we see that age was quite significant in determining the survival when through the PCA. And then when we look at PC component 2, we see that the gender was 95% significant for whether a passenger survived, yes or no. So this is just a tabular form. So we're just looking back and trying to get the percentage of each feature from each PC component. Then we're just gonna plot each PC component into a graph to visualize it. I can pop out. No, it doesn't look so nice. Zoom in. If it zooms in, it didn't
So great. This was the deciding graph. Gaith and I were having a calm discussion on whether we should have PCA as a separate chapter in our book. And when he saw this plot, he got it. He was like, oh gosh, yes, because this really, imagine everyone, you're going to stakeholders and you've said, we ended up using PCA features to feed our predictive model. Now they want to understand the model better. This is the graph you would show them. So you could, they would begin to get a feel for, oh, yeah, I see actually all these features, all the original space features are important, but what's really crucial is I see, age ended up being super critical in the eigenspace. Yeah, I love it, Jonathan. Great job. Now, I'm not trying to take your thunder away.
No.
If I understood correctly, you did leverage this from someone else's work.
Yeah, and unfortunately, there was no name at all to be found. So yeah, we'd like that, which was really unfortunate. So
yeah,
it's
I'd love to give the guy credit, right?
Yeah,
or the gal credit.
Yeah, it was a really thorough. Also using the Titanic, and once you've got your PC components, it really went into depth on going into the different models and feeding that and doing further reduction. So unfortunate that we don't know the name or the person, but from that you can then start saying, okay, well, looking at these, I see definitely I'm going to take age into my model. Did I have siblings? Was class a factor? Yeah. So how much was it a joint, fare? You could look in a bit more in depth and say, oh, well, fare was quite significant. Okay. Then you can take your fare into your model, and then you can say, well, I want passenger class as well. So just looking at those 1, 2, 3, 4 alone, you could run your model and see, okay, did they survive? Yes or no? And then what you could also do after this is then start iterating through the features. You could keep these as a base, and then you could iterate through by adding the ones that were less significant, just to see how your model generalizes. So it's not to say that, okay, yes, I'm going to take 100% these. You could say, well, these are my staples, but keeping in mind your correlation as well. So you could say, okay, well, this is my staple. I'm going to iterate through, add in some of the other variables to see how the outcome is.
Real quick, Jonathan. So right now, this visual shows, for example, PCA1 would be a combination of these quantities of original space features.
Yep.
But you could go the other way too, correct? You could create a visual that said, oh, original space feature 1, in other words, P class, would appear in these quantities of PCA1, PCA2, etc. Correct?
Yep.
It'd be the transpose, matrix operation or matrix multiplication. Very good.
Yep. So that is the end of the notebook, but yeah, it is very, very, very handy to pull that and definitely look at PCA. I think I might have another notebook that was running. Okay, yeah, this one.
If you could go back to that visual one more time, the final visual. So that's the mic drop moment, right? This is the ta-da moment right here. This visual and the inverse of this visual, that's the real ta-da part, correct?
To translate back the eigenspace back into the original feature. Yeah.
Excellent.
And
Please
then there was another chart, and I can't remember it, and for some reason I have broken the code.
I feel your pain.
There's another one. Oh, maybe this is it. Okay, so this is so this one did actually run. So there is that it. I think this one there, I was trying to plot the PCA groups. I don't know if it will run properly. Because but after looking at the PCA, so I took all the models and ran different models using what PCA came out with and what I thought would be it. Some of them are very close to each other, and as you can see here, this I ran into the same. So, and then there was one here was the PCA in XGBoost ran better, just using what PCA was throwing out, but then when you just took it out of the eigenspace and just ran it separately, you got a 86. You're on mute, Tom.
I only said very good. Y'all should have said, oh, Tom, we read your lips. Why don't you like it? That's our new family rule, remember? someone's on mute starts talking, we have the right to do bad lip reading.
Yeah.
No, this is great. Yeah, and I'm glad you brought this up.
Probably one of the reasons why the PCA model scored better was because all the features are separated. There's no collinearity in it.
Exactly. And I want to point out to some, and you see on some of these model techniques, it didn't matter, right?
Yeah.
Or it was almost, if we did a A/B test, it'd be insignificant. But
yeah.
and however, XGBoost is a really important classifier that often does best. XGBoost will even kick the butts of neural network architectures, and so I'm not surprised to see that was the highest model. But I was going to ask you something, and I forgot. But this is really good.
And that was just something that learned from your lessons as well. There, when you do PCA, you also have to remember that it's because it separates all the features into its own, that it removes all that collinearity from the features.
And exactly, Jonathan. And one point I think we want to make. I've shown you all visualizations. In fact, maybe I should bring those up. No, I showed them last week. But the spirit of, don't think that PCA is reducing your dimensionality. Because if you take your reduced number of PCA features and transform them back to original space, what you find is you have even more collinearity. It did not get rid of collinearity from the original space, just in the PCA space. But yes, the parsimony of the model being fed PCA features is better, but the overall parsimony of the pipeline is not better. We still have the burden to explain what happened in the pre-modeling pipeline. And that's why this plot you showed, that this extra work you did here, that's why it's so huge, so important. Well, let me share, and I'll take us to the next phase. Oh, any questions for Jonathan? And Hitesh, I thought you would like that plot. Sounds like your question was answered. Okay, I'm going to show something briefly that'll set us up good for next week. And this is what I'm about to show. I'm going to warn y'all is just super basic, and I really mean it to be. So, I've got to find the right thing. I believe this is it. Are y'all seeing my mouse move around here? Oh wait, I haven't shared it yet. I've only.
No, I was going to say we haven't seen it.
My bad. There we go. Yeah, now it's showing me that I'm sharing this one. So I'll go ahead and bigify this, as we say in my family. All right, let's do something ridiculously basic. I've got matplotlib, so I'm just getting ready for plots. And look at this. I create 2 points in a space and define X and Y for them on this plane. So literally, all I could do is the equation of a line. Now let's remind ourselves, that's all linear regression is. It's just when we only have 2 points, we literally can just get away with using the equation of a line. But I could throw this data into any of the scikit-learn models, and it would figure out the slope and the intercept. But this one's so simple, we could do it by hand. And sure enough, I did it by hand here. Here's what we learned in high school, maybe even junior high, how to get the slope of a line. And then once we have the slope, how we can get the y-intercept. So I basically just did that by hand. However, what's valuable about that, if that model for the line is accurate, I can predict the points in between. And so now I visualize that. These were the points that I used for training, and these were the points I was able to glean predictive value from in the future. So why am I doing that? I think if we see the stupidest, simplest example, it really drives home the point of what we're doing. Now, let's remind each other too, we don't like it when the data extend, when the predictions extend very far beyond what we trained on or very far below, because that's just not well-known territory. It's called extrapolation. And we typically don't talk about that much in machine learning because we don't ever do it, or hopefully we don't do it very often. But why does that not happen very often? Well, let's create some more realistic data. Still simple, but now we've done this a lot before. I'm just creating 100 points between 1 and 51. And I'm just looking at the first 5 to see what it gave me. It's just a random uniform distribution of points between 1 and 51. There's 100 of them. And I'm going to go into prophet mode, or I hate to say it, but God mode. I think God's going to be okay, meaning we're the creators here. We're going to create our own fake data, but we're aware of what we're doing so that we can completely understand the outcomes. And so I've reshaped the data accordingly, so it works well in the routines I want to use. And then I'm just saying here, we've done this before, I want a fraction of noise of 0.05. And what I'm going to do is take the max of my labels, the max of my Y values, and I'm going to multiply that by noise frac. And then I'm going to go from negative Y noise to positive Y noise, 100 values. I'm going to reshape them, and I'm going to add them to my Y. So now I have some noisy labels, and that's what this ends up looking like. Otherwise, all of these would have all these dots would have been on the same line, and you couldn't even tell that it was dots. It would look like a line, but we're adding a little noise for realism. Well, if I go into prophet mode, well, this is the model that originally generated my Y values based on my X values. And so if I do a scatter plot of my original X and Y, but I also do a line plot of X and Y prophet, look how it basically asks for uniform noise about these vertical axes. And so, yeah, that line looks like it passes right through. So let's not lose sight of the fact that if I import a linear regression model class from scikit-learn and I instantiate it and I say, yeah, go ahead and fit a y-intercept. I want to see what you get, and make a copy of the X data. Now I want you to fit the model. In other words, I want to know what the coefficients would be. And then I can go through here and figure out, okay, what are my coefficients? What's my intercept? Wait, what model bias is? Okay. And then we see that, oh, it was definitely a little off on the intercept. This is sometimes called bias. That's why I did that, to mix it up. The model bias, or the y-intercept, is 3.5. Well, we know from prophet mode that's not right, and that's okay. But we wouldn't have known that if someone had just handed us this data. This data. This data was just handed to us. We're doing the best that we can. But we can see that, that's off, but this is very close to 2, like we had hoped it would be. So oh, I'm sorry, my bad. We did add a y-intercept to this y-prophet data. So, forgive me. Where did I did it right here. I was thinking of another model, forgive me. So it actually did pretty decent. It's about a half a point off for the intercept. It's a little lower on the y, but that's because we only have 100 points. Well, as we can see, we don't do perfect when we're fitting a model. And again, we're in profit mode. We wouldn't have known this out in real world mode. But if we take this and experiment with, and this is just a lot of code, and I'll add this to our Google Drive. And by the way, we'll eventually add all these to the course repo too. But if I just start increasing the number of points over time that I train with, here's all that's going on. This is at different models with different numbers of points. So I'm literally instantiating this multiple times, but I'm changing the number of points each time. So what am I doing here? I'm going from 100 points to 100,000 points in 100 point steps. And I just wanted y'all to appreciate the more data we get, there's a point of diminishing returns, but somewhere around here is when, oh yeah, 40,000 points for this simple thing when we've got noise involved. It does keep getting better as you go way out here, but again, there's a diminishing return. Then I put it on a log scale too. Oh wait, this one. Oh, sorry, this is for the intercepts. This is for the weights for the first coefficient. And of course, we could do this for a much more complicated model, but it wouldn't increase the learning value that much. And this is me just putting the same on a log scale to help us appreciate, oh, you know, if we look at the center of this, we can see where it would have gone. And you could pretty much do the same with not being in profit mode. Now, what I want to show next week are two final things from my lecture series. It's going to be, how do here we're cycling through number of points for just to understand things better, but right at this point, how do we cycle through different algorithms? How do we cycle through different mixing the data set up so that we do cross-fold validation, meaning each chunk of the data set gets a chance to be the test set and the rest gets a chance to be the training set. So we'll look through cross-fold, and then how do we wisely cycle through hyperparameters? You see right here, well, I've got in different, depending on the algorithm, I've got different hyperparameters. I'm not even showing all of them for linear regression here, but for XGBoost, there's both number of estimators and the depth it can go, same for random forest, same for AdaBoost. If we get into neural networks, oh, how many layers do we have? How many neurons in each layer? What activation functions do we have in each layer? It gets quite complicated, the hyperparameters. So how would we cycle through those? And then we've got results from all these different algorithms and all their different hyperparameters using cross-fold validation. Oh, it's about to make my head explode. There's so many things to consider. How do we apply the metrics to figure out which model we want to put in production? So this was just meant as a stepping stone recap, because we've covered so much, and then we'll get into that kind of stuff next week. All right, take a break before we get into mentoring with Susan today. I'll stop sharing. Any